Now, once again, the webinar is going to be recorded. Thank you for joining. We are planning to make the recording available through the Neocortex website and PSC's YouTube channel over the next few days for your references. We also expect to have a 40-minute presentation followed by 20 minutes of Q&A. And we invite you to keep your microphone muted so everybody's experience is enjoyable. There are going to be opportunities to participate interactively during the webinar, including sending questions using the Q&A feature of Zoom, and also via completing the Zoom polls that are going to appear. This time we are going to have just a few with simple questions. I know our speaker is planning to just announce them and let you guys have some time to address the questions. The questions to the Zoom polls are going to be shared with the whole audience. And also then once you have asked and uploaded questions, we're going to address them in the Q&A session at the end of the webinar. We know many of you come through Exceed, and we want to let you know that this webinar abides by the Exceed Code of Conduct. Next slide, please. So here's a reminder of the Code of Conduct. There is a link for more details. This is our commitment to just providing an inclusive environment where everybody feels welcome, independent on any demographics. If you experience or witness any situation that might be a violation to this code of conduct, please make sure to contact any of the Exceed ombudsperson or report anonymously using the link that is at the bottom. With that being said, why don't we get started? So our webinar today is a technical overview of the Cerebras CS-1, which is the main compute engine for the Neocortex system. Our main speaker is going to be Natalia Vasilieva, who is the Senior Technical Product Manager at Cerebras Systems, Inc. And just to remind you, my name is Paula Vitrago. I'm the Principal Investigator for the project. And part of the leadership team at PSC includes also Nick Nystrom, who is co-PI and Associate Director for Scientific and Broader Impacts, and Sergio Sani-Levici, who is co-PI and Associate Director for User Support. Next slide, please. Our agenda today includes a brief overview of Neocortex. It's going to be just an introductory part that I'll be covering. And then we will have the Cerebras CS-1 technical overview that will be in charge of Natalia. Next slide. So a reminder, Neocortex is a project that was recently awarded. It's a category 2 system that is meant to be a testbed where we are testing innovative hardware that promises to revolutionize artificial intelligence, in particular the way we do training at the time. In the same way that Bridges AI and Bridges 2 is funded, and Neocortex has been funded by the National Science Foundation, and is a collaborative effort between the Pittsburgh Supercomputing Center, Cerebras, and Hewlett-Packard Enterprise. Next slide. The main goals of this project, which is 5-year long, it's to, on one side, deploy Neocortex in 2020. That's our goal. And by doing so, we are expecting to offer to the open science community hardware technology with capability that previously was not available for research, or at least not open science research. We also aim to research, explore, support, and operate Neocortex for 5 years. And one of our main goals is also to engage a wide audience and foster adoption via training and via allowing the access to this new system during the lifetime of Neocortex. Next slide. As a reminder, this is how Neocortex would look like. We have 2 Cerebras CS-1 systems. Each of them features a WSE, the Wafer-Scale Engine, of which Natalia will talk about more in detail in a little bit. They will be interconnected via a 100 gigabit switch, and they will be driven by an HP Superdome Flex with 24 terabytes of RAM and almost 200 terabytes of NVMe solid-state disk. Very fast interconnect in between the Cerebras CS-1 and the Superdome Flex. The Superdome Flex will also be connected to the Bridges 2 upcoming NSF system, where we will have even more access to larger storage for archival purposes, and also for doing pre-processing of data and similar pre-stuff. Go ahead, Natalia. Well, with that, I would like to hand it over to Natalia, who is going to talk about more about the Cerebras technologies that we plan to offer in Neocortex. Thank you.
Thank you, Paula, and welcome everyone. So I will start actually right with the poll, asking you how heavily do you use preprocessing and data augmentation. We've received a number of questions about these before the webinar, and I think the diagram, which is right now on there, let me just move it from the screen. Oops. The diagram which Paula describes on this slide, let me answer also that question. So we actually rely on SuperDomplex to run all the preprocessing. So that means that all data augmentation and data preprocessing techniques can be done on a standard CPU system, and they can take advantage of a very large memory of SuperDomplex. That system is unique on its own because it enables to keep large volumes of data in memory. How to get rid of this? Sorry. My setup is not working.
It's not advancing, the slide?
No, it's not advancing. Can you see the poll on my screen? It's right in front of the slide.
We cannot see the poll. We can see the pointer, the red pointer, Yuri.
Okay. Yeah, I think that's because there are several co-hosts, and so now I can see my slides too. I can continue.
Okay. Yeah, so, it's okay.
Yeah, so all the preprocessing can take advantage of this very large memory system, SuperDomplex. And I think one of the unique opportunities of the Neocortex system is this coupling of very powerful engine for deep learning, which is Cerebras systems, but also very powerful system for data analytics in general. And if you do use heavy preprocessing, if you do use libraries, and if you can take advantage of large memory systems such as SuperDomplex for this preprocessing, that's a unique Neocortex, that's a unique system for you to use. So now let's talk about what's beside those orange blocks and what's essentially hidden beside Cerebras CS-1. So Neocortex will have two of those, what it is. So the CS1 solution, CS1 system, essentially had three main components. A central one is in the center of the slide. We call it Wafer-Scale Engine. That's our very large processor. Essentially, that's the largest processor chip composed on a single piece of silicon. And I'll talk more about that processor a bit more. So this is the processor which enables all of the innovations on the kind of Cerebras and to run deep learning applications much faster and in much more flexible way compared to other existing processors. Because the chip is so unique, we also need a unique system to power, cool down, and bring data to Wafer-Scale Engine. And that's our CS1 system was specifically designed to do exactly so. And also we understand that hardware is not enough. We need to make it usable by programmers, by application developers. So software, our software platform or compiler stack is also an essential part of the solution. It enables you to kind of run code your models in TensorFlow, PyTorch, exactly how you used to do that, and use our software to compile it directly for execution on Wafer-Scale Engine. So I will talk about all of those three components in a sequence, but before, in a short quiz without poll this time, how many of you recognize what's that? If you have any background in hardware, I believe it's easy to recognize that's actually a picture of a wafer with the multiple dies on these. And essentially, their life of every chip, being processor chip or any type of the chip, starts from this. So every processor typically is printed as a separate die on the wafer. And then we kind of separate that wafer and package every die independently. It becomes a packaged chip. And for some workloads which require computational power of more than one chip, like it is for deep learning, many state-of-the-art models today require compute capacity of more than one common device. We spend a lot of time trying to bring those chips together. So we rely on distributed training or distributed inference. We rely on data parallel, model parallel training, essentially try to distribute the same workload across multiple processors. But as soon as you start distributing your work, as soon as you have multiple workers, those workers need to talk to each other. And essentially for any distributed work, communication becomes an overhead. And there are a lot of efforts going into hardware, into novel communication interfaces, protocols like NVLink or InfiniBand or extreme bandwidth, higher bandwidth Ethernet to simplify and to make it faster for those workers to talk to each other. But if you can recall again, many of those chips start their journey on the same piece of silicon. So they start being very next to each other. Why don't we keep them together? Why don't we keep them on the same wafer? And that's essentially what Cerebras decided to do. So we decided instead of cutting that wafer into dies and packaging every die separately, to build integrated connections in silicon between those dies and cut the largest square we can cut out of a wafer today. And essentially that's our chip. So this is Wafer-Scale Engine. And I said that's the largest processor chip of today. It's more than 46 square millimeters in size, has 1.2 trillion transistors. That's the largest piece of silicon being composed with the same chip. We use all that space to kind of put on the chip 400,000 cores. And all of those cores are optimized for a type of computation which you would need when you train or run inference of deep neural networks. And I'll talk more about that. Essentially, those cores are optimized to do really, really fast linear operations on sparse tensors. And that's the key operation, which is probably 90% of all operations which happen when you train a neural network. Those 400,000 cores are fed by 18 gigabytes of on-chip memory. All that memory is local to the processors, and that means that those processing elements, those cores, never starve for data. So you don't need to think about how to reutilize some of the data. It's always there very close to the compute. And it's also very essential, we have very high bandwidth, low latency connectivity between all of those 400,000 cores. So for us, it's very easy and straightforward to distribute workload across those 400,000 cores because we don't have to worry about communications overhead and don't have to worry about those bottlenecks. Because all of those cores, again, sits on the same piece of silicon. Connections between those cores are also on the same piece of silicon. And that means that we have very high bandwidth, low latency interconnect, and we can use any distribution strategy without any communication overheads to distribute the work across those 400,000 cores. So that chip is packaged and placed into our Cerebras CS-1 system, which is essentially delivers a cluster scale compute in a single system. We have one processor, one wafer-scale engine per this system. The system is roughly of the size of a mini fridge, but it also ingests the data with the 1200 gigabit Ethernet ports, and you can see them here on the picture. That's how our data comes into the system and also comes into the chip. System draws roughly 20 kilowatts of power. And that chip can be programmed using standard machine learning frameworks of today. The whole solution, including the Wafer-Scale Engine and system and our software, has been built from the ground up to accelerate deep neural networks. So we first thought about what the right solution for this workload would look like, and then we built the system. So I've mentioned that this Cerebras system is equivalent to a cluster scale, to a cluster of a GPU. So then let me ask you another question, like how many GPUs do you typically use today to train a single model? Okay, so all it looks like majority of you using a single GPU. There are still a few who use multiple GPUs. And I think what CS1 provides is provide the same experience as on a single system. So you still program CS1 as a single device, but at the same time you get performance of your cluster of a GPU. So you get speed ups essentially for free. Let me move forward. So let me start describing different components of the system, and I will start with Wafer-Scale Engine. So probably the right way to think about Wafer-Scale Engine is that it is a 2D mesh of 400,000 fully programmable processing elements. And when I'm talking about fully programmable, that's a truly Turing complete unit, which has local memory, so it has SRAM, it has functional and control units, which are specifically designed to accelerate sparse operations on tensors. And it is a data-driven architecture, so every single execution of any instruction on that processing element is triggered by the arrival of the data. Data arrives from the fabric on the chip, and essentially from either of the neighbors of that processing element. So if you look into inside that processing element, every single bit of this, each component of that processing element has been optimized for deep learning. So if we start from the compute, we have a fully programmable core. We have instruction set, which is kind of optimized for operations on tensors. But we also have instructions like common instructions, operational instructions for branching or some comparisons, so logical loops which you would need in any programming and on any device. It's also, as I mentioned, data flow architecture, so it is very well suited for sparse operations. Think about the memory. The memory is distributed across all of those 400,000 chips, so every single processing element, every single core has its own local memory, but it can be accessible from its neighbors too. So it is truly kind of shared distributed memory. And it is very well suited for training of deep neural networks, because type of objects which you would like to store on chip are typically model parameters, gradients, or optimizer states, which are local to the operations of a layer. And that means that typically instruction doesn't need random access to kind of all the data which is inside the model, but it needs only local access to the data which is essential for the specific application. And that design of distributed shared memory is very good fit for these types of operations. And then also essential third component is communication. So because again, our fabric is on silicon, on chip, we have very high bandwidth, low latency network between all of those cores, all of those processing elements. And that enables us to essentially use the same distribution strategies as you would use in a cluster. So do data parallel training or different flavors of model parallel training, or pick any hybrid blend between those distribution strategies in a very efficient way, because we don't have to worry about communication bottlenecks. This core also designed for sparsity, and the sparsity, what we call it harvesting, is enabled by essentially data flow scheduling in hardware. So every time, like what happens underneath the hood when the program is executed on CS1 on Wafer-Scale Engine. And I mentioned before that every single operation is triggered by the arrival of the data. So data arrives from Fabric and some packages which have either data or like control packages. It triggers kind of instruction lookup in the table of instructions, which were placed into that processing element in advance. It can also trigger the lookup of some local data, which lives in local SRAM. So in case of training deep neural networks, we will be looking up for model parameters, which are always kind of stationary and which are always kept on the Wafer-Scale Engine. And the data which arrives will be our activations, which travel through the network. And then both of these will kind of scale the execution of fuse, multiply, add operations. And then the output will be written back to either memory or sent through the fabric to the next processing elements for the next stage of processing. So that enables kind of intrinsic sparsity harvesting on the hardware. That means that if we keep sparse representation of the data, we don't spend our bandwidth to sending zero because we send the data in this sparse representation, in sparse format. And also we can make sure that no computation happens on non-sparse elements. And again, because we are talking about linear operations or linear algebra, implementation of that is quite straightforward. Let me show you some example, a synthetic one, to prove that CS1 can translate essentially sparsity to speed up in a very simple way. So we set up a very simple experiment when we have a synthetic, fully connected neural network with 34 layers depth. And then we kind of run that model on CS1 and on GPU, and we slightly modify the model. So we first started with a fully connected neural network and with all activation functions being identity. So it does make much sense from machine learning perspective because you can squash all the layers into single, but for us, it was important to measure the speed up which we can get when we add more and more sparsity into that model. Instead of identity function, it could be some other non-sparse non-linearity, such as hyperbolic tangent or jello, or whatever you use. Then we wanted to see how the system would react if we do nothing but change that non-sparse activation function to ReLU, which essentially zeroes out everything which is below zero. So your outputs, your activations become sparse. And as you can see from the slide, we can observe instantly the speed up. So sparsity translates to speed up on CS1. And that's not the case for GPUs. Then we're also working on some approaches how you can artificially induce even more sparsity into neural networks. And these days, most of the neural networks are kind of over-parameterized. So it turns out that you can add additional sparsity into activations or weights, and still without any implications on final accuracy and final convergence of the model. And because our system allows you to translate sparsity into speed up, so essentially we add this artificial sparsity without any effects on accuracy, and then we can just make the model run faster. So here we are showing gains in speed and throughput when we add this synthetic sparsity into workload. Our ML team also runs massive experiments on impact on this induced sparsity onto the models. And on average, I think we've found that for majority of the models we've been experimenting so far, adding 25% of sparsity doesn't impact accuracy. For some models, we can add more sparsity, up to 50, some cases even up to 75%, but with moderate impact on accuracy. And this just becomes another tool in the head of the user. So it's up to the user to decide what's more important to get this, I don't know, tenths of a percent of accuracy, or instead have the model trained 2 times faster. That's yet another tool which you can use with our hardware when you're training deep neural networks. So I've talked a little bit about sparsity. Let me ask you, do you actively use sparsity in your research? And essentially, what kind of sparsity you're experimenting with? Is it weight sparsity, activation sparsity, or both? Cool. It looks like sparsity is an interesting, at least for half of you, maybe even more than half of you. It's an interesting area of research, and I think in order to be able to leverage sparsity and to translate the sparsity to speed up, you need to have flexible hardware. So it will be interesting to see what we can do on Neocortex. So kind of summarizing advantages for deep learning for this Wafer-Scale Engine. Again, all 3 components, compute, memory, and communication has been built for deep learning workloads. That means that in terms of compute, we have massive compute. We have more compute that can fit on a traditional die. So that means that you get a performance of multiple processors. It is optimized for linear operations on sparse tensors. So that means that you can exploit that avenue of speeding up your training. And it's also very flexible because it's a data flow architecture, and because every single processing element can be programmed individually. So that means that you can run 400,000 different instructions and different data points at every single kind of cycle. And that gives a lot of flexibility to support models which are not that uniform, so which are not composed of kind of nice and square matrices, which has different operations, and not only like matrix multiplication, which you usually have when you do large batch processing. But you can also take advantage of things like separable convolutions, or things like kind of neural architecture search, which results in kind of non-homogeneous architectures. Memory is large hand bandwidth and tightly connected to the compute. What it means for researcher, that means that you don't need to worry anymore about batch size for your performance. You can train with whatever batch size makes sense for you. So if you believe that for a specific model, for a specific data set, it makes sense to use batch size of 1 or of 8, you can go ahead and do that. If you believe that for your problem, it is beneficial and the model will converge faster if you run with extreme batch size, maybe tens of thousands. It's also kind of easily supported out of the gate on CS1. You don't need to modify your code. We will just accumulate the gradients for a number of samples that you want to have in your mini batch, and we will do model updates once in a while. So it's a very natural way for us to operate. And our fabric is high bandwidth and low latency. So that means that we can pick up the right blend of distribution strategy, and we can rely on just the right amount of model parallel and just the right amount of data parallel execution for that specific model which we have in hand to fully utilize all 400,000 cores on the chip. And that means that like utilization of the hardware is always high. So we talked about the Wafer-Scale Engine because it's so large and it has so many cores. It was a challenge how to kind of cool it down, how to bring power to the chip. And let me spend just a little bit of time talking about the system. So our system, CS1, I mentioned that it's the size of a mini fridge. And essentially 3/4 of that mini fridge are there for cooling. So on the slide, you can see a rendering of the system. And I have my pointer. The actual compute part, so the Wafer-Scale Engine, our wafer sits right there. And occupies a very small fraction of the volume in the system. 3/4, like all the bottom half, and this quarter are for cooling. So the system has kind of 2 loops of cooling. We use closed loop water cooling to actually cool down the chip. And we also have 2 options, either to use facility water to cool our own internal water, or we can use air to cool down our internal water. And that enables us kind of to cool down the water which goes through the hot chip, cools down the chip. We get hot water down into the system, which is being cooled either by air or by another loop of water cooling. And this part of the system is responsible for bringing power to the chip, and this upper part responsible for bringing data to the chip. So here we have our 1200 gigabit Ethernet ports. That's just another nice rendering of the system. And now you can see the heart of the system. So Wafer-Scale Engine, which is essentially sandwiched between a motherboard and a cold plate. And motherboard is used to kind of, again, deliver power and data to the chip. And the cold plate is used to cool it down. And then blow up picture of that key part of the system. So now let me spend some time talking about the software and how you can program that chip. I mentioned that it is as easy as program a single device, as a single CPU, a single GPU, but how we actually achieve that simplicity. So we achieve that with our software stack, which has several components. So when you first present to our compiler a code written in some of the familiar frameworks, such as TensorFlow or PyTorch, we will extract kind of graph representation of your workload, and we'll convert that to our intermediate representation, which we call linear algebra and intermediate representation of layer. So that will be a starting point for us to go through the rest of the compilation, and that's where all the dependency of the framework kind of ends. So whenever there is, let's say tomorrow we have a new PyTorch, or we have a new framework, the only thing which we will need to have, which we will have to do in order to support that on CS1, we'll need to write that converter from the internal representation of that framework into layer. And the rest of the compilation process we can stay intact. So once we have this computational graph in our internal representation, we go through the next steps on how to kind of match subgraphs of that computational graph into our kernel library. Kernels essentially are small programs written in a low-level language to be executed on our chip, and those small programs implement small portion of neural network. So they will implement typical subgraphs. So you will have a subgraph for a fully connected layer. You will have a kernel also for something like LSTM cell, or for something like attention. You will have a kernel for kind of common nonlinear activation functions, and for a bunch of other building blocks which are typically used to compose the neural network. So once we've matched that to the kernels, then we place and route those kernels on the fabric. So we decide how many processing elements, how many cores each core should get. So how it depends on the computational complexity of that kernel. And then we also configure on the fly the network on the chip so that we can maximize their communication between those fractions or those sections of the fabric which should talk to each other for this specific model. And then at the end, we link everything, create executable, which can be placed on the CS1. Just one comment, so this whole compilation process happens on a standard CPU. So in case of Neocortex, the compilation will happen on Supercomputing flags. And once we have an executable, then our software will kind of load that onto CS1 machines, will program the fabric, and it will be ready to start training or inference. Going a little bit more into the details, how it looks like. So I've told that the first step is to extract model from the machine learning framework and then to convert it to linear algebra intermediate representation. So as you can imagine, every computation can be represented in the computational graph. And for neural networks, it's a quite common representation to represent your neural network as a kind of graph of computations. So once we have this computational graph, again, we just use our own representation to keep or to store that computational graph. The matching operation will look into our kernel library, and every kernel in our kernel library kind of advertise types of the subgraphs which it can implement, like the corresponding subgraphs. So we'll parse the computational graph which we get from the researcher from the beginning of the compilation process. We will go through the compilation through our kernel library, and we will find the kernels which match portions of that computational graph. And at the end, we will get a kernel graph which will have much less nodes than original computational graph, because instead of every single summation or every single multiplication being a node in that computational graph, we'll now have kind of bucketed them together. We'll have one kernel representing a subgraph in the original graph. What happens if some parts of this original computational graph don't have a match in our kernel library? When if there is a missing kernel, if you come up tomorrow with some sophisticated activation function which we haven't think about and we don't have a handwritten kernel for that, or if you come up with a completely new type of layer, what happens then? In this case, we can use our kernel compiler to generate microcodes on the fly. So it will synthesize a microcode which will implement the operations in the original graph which are not covered by handwritten kernels. The performance of that synthesized kernel would be probably lower compared to the performance of the handwritten kernel. But at the same time, if it's just a small portion of the overall computational graph, typically the difference in performance will be negligible. So we use today those synthesized kernels for things like new nonlinearities or for some other small components without impact on performance, or with very negligible impact on performance. So now once we have this kernel graph, how that get placed onto the chip? During the placement operation, we look at algorithmic complexity of every single kernel. We understand how many flops underneath that operations, that operational subgraph, and we decide how many processing elements on the wafer should be allocated, so that at the end, if we run that execution in a kind of layer pipeline mode, where we have placed all of the layers of the neural network, all of the kernels we place at once on the chip, and then we kind of run that as a conveyor, as a pipeline. So we have the very first sample coming through the first layer, then transitioning to the next one, and while the second layer operates on the first training sample on the first mini batch, the first portion starts processing the next piece of data. So for that, for us, it's important for this layer pipeline execution, it's important to keep that pipeline very balanced. So right sizing of their sections of the fabric, which will be allocated to different kernels, is very important. So once we solve that optimization problem, once we understand kind of how many processing elements should be allocated per kernel, I mentioned we configure the fabric. So we make sure that we maximize the communication wires in between the sections of the fabric which send data to each other. Here's an example of placement of a real model using one of our visualization tools. So every single rectangular here corresponds to a separate kernel which could implement a standard operation, standard layer neural network. So typically you will see we'll have an input layer along one of the edges of the wafer because data comes from the edge. And usually the smallest area will be allocated to loss because computation of loss is usually not that compute intensive. And then the area of other rectangles will depend on the computational complexity of every given kernel. So here, for example, we see that there are two layers which have very different footprint on the wafer. That probably tells us that the computational and algorithmic complexity of those layers is quite different. And after the routing, essentially what happens during the forward pass, we will get our input data. The first kernel will process that and send the output, then the activations to the next layer, and so on and so forth. And again, we will configure the fabric on the chip in such a way that it will be maximized for the areas, for the sections of the fabric which should talk to each other. So in this picture, for example, those two guys, these two never talk to each other, so there will be no links configured to bring data between those. So that's the picture of the forward pass, and on the backward pass, it's just in reverse order. So we'll send deltas and compute gradients for the model and backpropagate all the errors in backward direction. So in summary, the compiler stack performs the following operations. So we extract the graph from the machine learning framework. We have linear algebra kernels, which are mapped to the subgraphs of the original graph. These kernels are kind of sized and placed corresponding to their algorithmic complexity, and to keep the pipeline balanced and to maximize the throughput of all layers. Then we configure the network fabric, so we route it to maximize the communication between those sections of the fabric which should talk to each other for this specific model. And I mentioned, like, key kernels are handwritten and hand optimized, but we also can generate kernels on the fly for those parts of the original computational graph which don't find the match in our handwritten kernel library. So essentially what happens when you do the compilation. So after the compilation is completed, you have an executable, which is copied to CS1, and every single processing element is programmed with the instructions, which should be kind of executed as soon as input data is there. And when their Wafer-Scale Engine is programmed, so we have all instructions loaded, the fabric configured, every single core knows what to do depending on which data it receives. And then we just start streaming input data. And we stream that, and the training or inference process starts. So I have a few minutes maybe left to talk a little bit about specific advantages of CS1. So CS1 is designed to deal with the large scale model, but also to unlock kind of new model techniques. And it's designed to scale, because you can think of CS1 as just a much fatter single node, single device. So it can replace mini cluster of GPUs, and it is as easy as program as a single GPU. So whenever you need to go to extreme scale and to go to very large models, yes, we can scale out. We can use different wafer-scale engines, but you will need less of those compared to GPUs. But what's also unique about CS1 is that its flexibility. So the fact that it is a data flow architecture, and we have flexibility essentially stream data at a very fine granularity. So for natural language models, we can stream token by token. For computer vision models, we have some prototype and work when we stream them pixel by pixel. So that enables us to harvest things like sparsity at a very fine granularity. So if you have a like sparsity on token or on pixel level, we can harvest that efficiently on CS1. And the second key property is that CS1 is essentially multiple instruction, multiple data architecture. So I've mentioned at the very beginning that every single processing element can do independent instruction on independent data point. And that enables us to also kind of efficiently execute models with, let's say, conditional execution or adaptive depth, or some other novel techniques which are designed to reduce the algorithmic complexity of the model. So CS1 has that flexibility at scale and scale at the same time. So kind of summarize from the user perspective, with CS1 have this massive accessible performance, which has advantages from different layer or different angles. So from the kind of system point of view, you don't need to worry about cluster. There is no communication bottlenecks. For a user, it's also much easier to train on a single device. For a machine learning researcher, since you don't need to rely on data parallel if you want to scale kind of out, you don't need to think about low utilization, lower batch. You don't need to think about different optimizers because you're not forced to train with very large batch size. It has flexibility for new models, new generations of models, for things like conditional computations, for sparsity induction techniques. And essentially we can deliver ultimate performance with a cluster of those. And we will have two CS1s attached to SuperComputing on the Neocortex. So it will be interesting to see what can be done in a distributed setup sometime in the future. So in summary, the system has been built to accelerate training and inference of deep neural networks. And with the goal that it will empower researchers to generate more ideas, of how the model could look like, generate new ideas about different optimization algorithms, and which are not necessarily rely on kind of batch processing and when you do exactly the same operations on the same data. So back to Paula.
Thank you, Natalia. Thanks for a great presentation. That was a very interesting technical overview of the different elements that are part of the CS1. I have seen our participants are very actively sending questions and comments through the Q&A. Please send more or about the ones that are already up there so we get ready for our Q&A session. I would like to remind everybody that if you want to learn more and participate on the Neocortex project, you can make sure to review the upcoming events in our PSC Neocortex website. Also, there is an upcoming early user program that we will be opening anytime soon. We, in general, just publish all the updates and relevant new announcements on the website, so that's definitely the place to go. And also, if you have any questions, input, or requests, feel free to always contact us at neocortex@psc.edu. Next slide, please. And with that, I would like to thank you all of those that are contributing to make Neocortex possible. This is a collaboration between PSC and Cerebras and Hewlett-Packard Enterprise. And here in the bottom, I'm listing just the group, well, the team at PSC that is contributing to getting up the project. With that, I think we are ready for the Q&A session. We will have Nick Nystrom facilitate the conversation. Nick, whenever you're ready.
Yep. Hi, Paula. Thank you very much. I've been trying to keep up with the questions. This has been a really good group with a lot of great questions. And so I'm going to try to, in the time remaining, to highlight the ones that have got a lot of attention and that really deserve a live answer. We're still catching up on answering a bunch of those in chat as well as written answers, and we'll follow up after the webinar with all of these on the Neocortex website. So I think the first question I'd like to take live, there were a number of questions early on about yield on the Wafer-Scale Engine and how it handles any defects that inevitably occur. So I'd like to ask Andy Hawk of Cerebras to address that one.
Happy to. Thanks, Nick, and hi, everybody. Thanks for attending the webinar today. My name is Andy Hawk. I'm the head of product at Cerebras Systems. The Wafer-Scale Engine was designed with multiple levels of redundancy throughout, both on hardware and on software. And principally, with respect to hardware, we've provisioned additional redundant cores and lines of communication. So while we quote a spec for each production wafer of 400,000 cores with a 2D interconnect mesh, in reality, we have additional cores, more than 400,000 on the device. And we also have some connections, some skip connections and diagonal connections on the on-chip network fabric that allow us to detect and then route traffic around bad cores that may have been knocked out by regular in the manufacturing process. So what happens, practically speaking, is we'll get wafers back from our fabrication partner, package and test them, and at bring up, our software on the CS-1 system detects any defective cores and routes around them in software, so that what is presented to the user and to our compiler software is a uniform grid of a standard set of cores. Not only does that protect us against defects from manufacturing, but it also protects us against any expectedly very rare issues that we may have with individual cores or processors during the life of the device. So in practice, what this means is that we've been able to yield effectively every wafer that we get back from the fab into a production system.
Okay, Andy, thanks. It's impressive the way this works to get yield on a whole silicon wafer that is effectively 100%. So I'd like to jump now. There were several questions that were upvoted.
This project was very ambitious, but
you just went mute.
Yeah, sorry, I was just going to add to that this was the Wafer-Scale integration project was a really ambitious one, so we had to keep in mind the biggest risks, and of course, accounting for manufacturing defects and yield is one of the biggest risks. And the unique nature of our chip architecture in this uniform 2D grid of identical cores gives us some advantage in terms of resiliency to manufacturing defects and other types of issues that might occur. We tried to design that into the beginning.
Okay, thank you. So moving to some of the other questions that have been upvoted and not answered yet. There were several questions on compilation and essentially the software stack. And so I think, Natalia, I'd like to address these to you. And there's one on how does a system optimize conditional compilation? And on a related note, how does compilation and routing work with non-sequential models, such as functional type neural networks?
Yeah, so first, I believe probably was conditional computation. Essentially, that's what I meant. There are some new breeds of neural networks which rely on kind of conditions inside the model. Depending on their specific input or training sample, you will route to one kind of branch of the model or another branch of the model. Good examples of these are recent humongous language model trained by Google, which has 600 billion parameters, which uses several experts, how they call them, in between of their model. It's also kind of BERT transformer type structure. But every single mini batch, every single sample is used to update parameters only of a small subset of that model. Because if you would use every single sample to update kind of all of the parameters, training of that model would become completely infeasible. It's too large, too a lot of compute. Another example is ideas around universal transformer, ideas around dynamic depth, where you essentially build a stack of the layers, and depending on the input, you decide how many transformations you want to go through for that specific input in order to get to the right representation. We're talking about language models, and every, like an input is a sequence of tokens, a sequence of words or parts of words. Some of those can be ambiguous. Some of those can be very simple ones, like I don't know, cat or dog. It will be very hard to kind of, the representation of the word is dog, or maybe it's not a good example, but there are some words, representations of which won't depend that much on the context. It always has the same meaning. So probably you don't need to go through, I don't know, 20, 40, 100 layers of transformation to get from the original embedding of this token into something which represents its meaning. For some other words, they could be very ambiguous and they could depend a lot on very long context. So in order to find that right space in the high dimensional space of those, right point in the high dimensional space of those representations, you would want to go through multiple layers of transformation. And conditional computations allow you to do just that. So for some inputs, which you think it doesn't make sense to kind of process them, you just stop processing. And for some, you go all the way through. And for single instruction multiple data for simple engines like GPUs, it's very hard to support that because they essentially like to do exactly the same operation on all of the data. So you treat data in the bulk of sequences, and you want to do exactly the same operations on all of the tokens of all of the sequence in a batch. You can use padding to kind of hide that, but it still will be like missed cycles on the hardware. And on CS1, because again, every single core is programmable, we can kind of smartly deal with that and don't do operations where they're not needed. I hope that answered conditional computation. The second one was how we can deal with non-sequential models. So models like many computer vision models or some other models, they don't have to be sequential. Maybe I misunderstood the question, please correct me if I'm wrong. But any neural network is essentially a sequence of transformations. In my understanding, sequential model is something when you deal with sequential also data, and when you have dependencies on the input. But for all others, it could be quite complex graph of transformations, but they still happen one after another. It could be complex connections, but we can map all of them on the wafer, and we can also place the layers which should communicate to each other, even when there are different skip connections next to each other.
Okay, I'd like to jump to the next cluster of questions. There were a number on performance, as you would expect, and performance efficiencies and energy efficiencies. And one thing that, having closed the system, I recognize is that its way of handling sparsity means that the operations it does are much more meaningful. They're necessary. It's not spending most of its cycles multiplying by 0. But for those that are asking about what's the performance, have you compared, or have we compared against other systems like DGX2? What's the best way to think about all that, Natalia?
So internally, we don't have DGX2, so we didn't run any tests ourselves. But many of our customers do. So they do own clusters of GPUs. They own DGX systems, DGX1s and DGX2s. And for us, probably the way how we compare performance is we have a customer who comes to us and tells that, here's my model. I run it today on, I don't know, 4 GPUs, 8 GPUs, 16 GPUs, so whatever cluster he has today, whatever system he has today. And my performance is X. Show me what you can do on CS1. And then we take that model and we run that on CS1 and we see. So when we compare in that setting for different customer models, we've seen speedups for kind of multiple tens to multiple hundreds, mostly depending on the footprint of the GPU cluster where we compare to. So for those customer workloads, we've seen like multiple tens, multiple hundreds, orders of magnitude speedup.
Yeah, I would say for
family of models.
Yeah, I would say for those who are interested, join us for our early user program, and part of that program is helping you get your models running well. So,
Nick, if you let me just one single comment. Also, most of the models have been designed to run on GPUs. So to me, I think handing something like Neocortex into the hands of researchers and giving them access also means that we can enable all of you to think what kind of models can be designed for CS1 and maybe run much, much faster than you can do on GPU, but they will take advantage of the specific architecture of CS1. So we are very interested in collaborating with all of you.
Yeah, that's a great point. Go ahead, Paula.
Sure, Nick, if I may add something.
Yeah.
So as some of you might be aware, on Bridges AI, we do have a DGX2, and we are actively exploring 2 use cases that we define in collaboration with Cerebras and testing how fast do they run with the full DGX2, which later on we will compare with the results that we get on the in the CS1s in Neocortex.
Yeah, and that's true. And one point I'd just like to add on to Natalia's comment is, for those of you who are thinking about using Neocortex, don't be afraid to think big. Think beyond what you can currently do any other way, and that's what this system is for. So it's about getting large science done, no cost for open research, and please keep in touch with us and look for the early user program. So the other thing, I'm just quickly getting back to the questions. I think we have time for one more before we run out of time. The rest we will answer online. Check out the Neocortex website. They will be there. So other questions that, I made a mistake of changing windows. Yes, another cluster of questions is important to address. I guess mainly Natalia, is for big models that may be too big even for a CS1 and its massive SRAM. What's the plan for handling those?
Yeah, the current plan for handling them and what we experiment is scale out. So the answer is the same as you would have with any other device. It's just we need to start scaling out this later than what you have with the GPUs. One other kind of point which I want to make is that we get that question pretty often, and we get the question why you choose to not add more memory into the chip. And I think the answer is because we believe it's importance of the system being balanced. Even if I had like a magical wand and I could add an unlimited amount of memory on CS1 today, even having on chip, and I can suddenly feed, I don't know, multi-100 billion parameter models onto the chip, I would probably still use multiple systems to train that because it will take eternity to train them. You need to scale kind of at the same pace, memory and compute. So we believe that for those large models which don't fit onto the system, you would scale out anyway, just because of the compute reasons, not because of the memory reasons. And we believe that the system has the right balance of compute and memory. And for larger models, we just need to scale them into more systems.
And that's why we invested in 2 CS1s, to be able to explore that and start down that road. So I think we're out of time. Paula, back to you.
Sure. Well, thank you everybody for participating, coming to this webinar, learning more, and also all your questions, add votes and comments. As Nick mentioned, we will following up by basically publishing all these questions and making sure they get an answer and just posting them on our website. So if your question for some reason could not be addressed in time, within the time that we had, we'll let you know once the questions are all answered on the website and you'll get your answer. So thank you all. With that, I would like to conclude the webinar. Thank you. Well, before that, I would like to say thank you to Natalia for a great talk. And now with that, I would like to conclude the webinar and thank you. Stay safe, healthy, and look forward to the next opportunity.